Okay, so we are moving along in our bonding notes. Let me hide my floating meaning controls here. Is that what I needed to do? Okay, that's what I needed to do. All right, so intermolecular attraction. All right, let me turn off my announcements just in case they're going to start announcing lunches any second. All right. So intermolecular attractions, right? So sometimes we refer to these as IMA, right, for intermolecular attractions, or intermolecular or IMF, right? So we kind of use these, and then the F would be, instead of intermolecular attractions, we would say intermolecular forces, right? Because attraction is a force between what, right? Between positive and negative objects, right? Magnets are attracted, right? So those is a force between, magnetism is a force between those two magnets. All right, so when we talk about intermolecular, we're talking about the attraction between molecules, right? The force of attraction between molecules. Inter meaning between, molecular between molecules. So when I take apart the word, it literally means the attraction between molecules. And we have three main types. The one that you really need to make sure that you know the name of is going to be the hydrogen bonding. I don't think you're going to be as specifically asked dipole or van der Waal, but let's break apart this word. And I like to kind of throw some quotation marks here around bonding, because it's not really a bond. It's really a intermolecular force, but it's very strong, almost as strong as a bond. So dipole, which the prefix di means two pole. So basically a two pole attraction. And remember, pole means different. So a pole of a magnet, right? So then I have dipole. So I've got something that's positive and negative, and then it's attracted to something else that's positive and negative. Okay, so we're going to go through a slide on each of these types of intermolecular attractions or intermolecular forces. So we're going to first talk about our dipole, right? So remember how I said two poles, right? So two poles, right? And right, I've got a positive and negative pole, and then I have another positive and negative pole. And so it's a force of attraction defined between adjacent, wait, what does that word mean? Next to polar molecules, right? If I have two polar molecules near each other, there's going to be a force of attraction between the two, right? Polar molecules, remember, polar bonds can either make polar molecules or they can make non-polar molecules. And then whether or not something is polar always depends on the shape of the molecule, right? So SNAP, symmetrical, nonpolar, asymmetrical, polar. So when there's an unequal sharing and distribution of electrons, right, that means polar, right? That's the definition of a polar molecule, so polar molecule. Making one end of the molecule seem positive and the other end seem negative, right? That means our partial positive and our partial negative, right? So our delta positive and delta negative. Remember, that's funny looking, incomplete 8 looking thing is our lowercase Greek letter delta. It means partial positive and partial negative. So here I have inter, right? Because the prefix inter means between. Intra just means within. So then this is the attraction, right? So there's a shared pair of electrons here, right? So dot and dot, shared pair of electrons there. Let me just erase that. I don't really like how that really looks. Okay, right, we have a shared pair of electrons, right? So then this is a shared pair of electrons, and it is a polar bond, right? It's a shared pair, so 2 total electrons, 1 shared pair. So then that is the sharing or attraction within the molecule. But since this is a partial positive and the chlorine is a partial negative, Why is chlorine, again, the partial negative? Because it has a higher electronegativity value, right? So ENV, or EN for short. So that means the attraction for electrons are stronger. So that means that the electrons are getting pulled in that direction. So that gives it a partial end. So then one partial end and another partial negative end and a partial positive end is going to attract, right, positive to negative. So then that's where this intermolecular attraction comes from polar molecules. This is what holds liquids together. So this is what holds water together, for example, is a pretty strong dipole-dipole attraction. And so the strength of that attraction depends on how partial positive, how partial negative, and it depends on the elements that make up a compound. And these forces of attraction are going to influence boiling point, and they're going to influence melting point, obviously, if melting point, so boiling point and melting point, and phase of matter. Right, so if something has very strong, so maybe I'll jot this up here. If I have a really strong intermolecular force, you're going to have a higher boiling point, melting point, and maybe, you know, a stronger phase, right? A solid or liquid versus a gas, for example. And when we do our phases of matter unit, we'll talk more about that. And so now we have our second type of intermolecular force. Again, we're talking an intermolecular force, or, you know, intermolecular attraction, right? IMF or IMA. And I like to do hydrogen bonding because it is not a polar bond. It is an intermolecular attraction, an intermolecular force. It's a force of attraction and not a true bond. It's not a covalent bond. So when hydrogen is bonded to a very electronegative element, right, these are our top 3 electronegativity elements, right? We want to look at table S, right? Fluorine being the highest with the 4.0. And oxygen, I think, is like a 3.2. And so we like to say hydrogen bonding is fun, F-O-N, right? So when hydrogen is bonded to fluorine, oxygen, or nitrogen, we get a very, very strong intermolecular force. And that's a very special kind of intermolecular force called the hydrogen bonding. So the hydrogen end seems positive while the electronegative end hogs and seems negative. So it's much more negative, much on one side than a regular dipole-dipole. So hydrogen bonding is a dipole-dipole attraction, but it's a very strong dipole-dipole attraction. So strong, it's got its own name, hydrogen bonding. So it's responsible for the relatively high boiling point of water, right? Water is a pretty tiny little molecule, right? H2O, right? So 2 waters and 2 hydrogens to one oxygen, right? And it's got a gram formula mass. It's really small. It's only 18 grams per mole, right? It's a tiny little molecule. It has a boiling point of 100 degrees Celsius, right? That's really high, which is 212 Fahrenheit, which is also, you know, is very high. 373 Kelvin, if I, you know, got to give Kelvin his credit too. So what we have here is we have our polar bond, right? And we have this polar bond between oxygen and hydrogen, right? Oxygen has a very high electronegativity value, right? It's in the top 3, right? Hydrogen bonding can only occur with fluorine, oxygen, or nitrogen. So we say hydrogen bonding is fun, right? Which is kind of like a play on words, and, you know, I get to be super nerdy when I say all that stuff. But really, this is not the hydrogen bond. The hydrogen bond is here, right? Because this is the hydrogen bond right here. I don't want to make that a line because I don't want you to think that it's a, oops, not highlighter. I wanted eraser. There we go. Okay, so I'll end up circling it instead here. So this is the hydrogen bond right down here. This is the hydrogen bond. This is another hydrogen bond between water molecules. This is what holds water together. This is why water forms the droplets that it does. This is what allows, raindrops to hold together. If you were to put a drop of water on a piece of like wax paper, for example, or aluminum foil, it's not going to spread out. It's going to make like a very, concave round drop, right? So when water forms this really round droplet like that. But if I were to do something else, let's say like nail polish remover or rubbing alcohol, and I were to put a droplet, it's not going to be as nice and round because it has much weaker hydrogen bonding. It has much weaker dipole-dipole attractions. So it's going to be more of like a flatter droplet. And so this is why water has such a high boiling point for being such a small molecule. And this also then contributes to why water can absorb so much heat energy with that really high specific heat as well. And so then we get into our London dispersion forces. You don't need to know the term London dispersion forces, but this is a force of attraction between adjacent, let me move that up so you can see that word, adjacent nonpolar molecules, right? So a nonpolar molecule, remember, symmetrical is nonpolar, asymmetrical is polar. So we're talking about a symmetrical molecule here due to the uneven distribution of electrons in otherwise symmetrical molecules. So let's take a look here. These are the weakest of intermolecular attractions. And these are mostly going to be the type of attraction that we see in gases, right? Because gases have pretty weak forces of attraction. And again, my handwriting is atrocious. All right, so we'll just leave that as gas. Okay. So we have here this nonpolar covalent bond. Right, this is chlorine, right? This is chlorine, right? Cl2, it's a nonpolar covalent bond because it's not different nonmetals. But what happens is there are those electrons on the outside, right? Because when we draw the Lewis dot diagrams, right, we still have those lone pairs of electrons out there. Well, sometimes these electrons that are in this bond right here might just for just a brief moment in time, because remember, electrons are in constant motion. They are in orbitals, right? They're kind of like swarming inside around the nucleus, and they're really fast moving particles. They might temporarily kind of hang out closer to one end than the other, making a very temporary pole. And so then there is some very weak attraction, right? This allows us to move through air, right? But if you try to walk through water, right, like in the shallow end of a pool, if you're trying to like walk from one end to the other, you're going to feel some resistance because first of all, those water molecules are much closer together and they have a strong force of attraction to each other. But as you're walking through air, you're not really going to feel the force of attraction. You're going to feel some of the particles move out of your way, where you feel a little bit of wind resistance, but you're not going to feel that strong force of attraction because they have a very weak force of attraction between the two, which then is why gases have such a low melting point and a low boiling point. And so we get into now what we call an ion molecule attraction. So what is an ion? An ion is a positive or a negatively charged particle. Right? So some of these things that we've learned from before, right? They tie in together. As we move through the rest of the year, things will start kind of fitting together more, and things I think tend to make more sense, I think, as it builds. So I have an attraction between an ion and a molecule. Okay, so an attraction between a molecule and some sort of charged particle. So in an aqueous water solution, ionic solutes dissolve. So we have the positive ions, which are our cations, right? So our positive cations of the solute. So then we'll get more into this when we do our solutions unit, but this is usually what is being dissolved, right? Usually we're going to talk about a solid here. Attracted to the oxygen end, which is the negative end of the water molecule, right? Because remember, the water molecule has those poles, the partial positive and the partial negative. And now we have our negative ions, right? Those are our anions of the solute, right? The solid we're trying to dissolve are attracted to the hydrogen end because that's going to be our partial positive end of the water molecule. So here I have sodium, which is positive. And so here's my water molecule, right? And so this here is our hydrogen. and this here is our oxygen. So the oxygen has a higher electronegativity. So this is why this is my partial negative end. So when we put salt in water, so NaCl solid, let me erase that and write that somewhere where I have a little bit more space. Okay. Just so that I can make hopefully my handwriting a little bit better. So let's look at sodium chloride as a solid. And I'm going to dissolve in water. So then my little arrow means a little change. It means something's happening here. And when I put an H2O on the top, that means dissolve. So when it dissolves into water, it splits into ions. This is why the ionic compounds dissolved in water conduct electricity, right? We'll call those electrolytes. So it splits into that aqueous, now dissolved in water, positive sodium ion, and our aqueous chloride ion, which is negative. And so the water molecules surround the sodium chloride and kind of rip it apart, right? Because the water with that hydrogen bonding has a really strong force of attraction. It's got a pretty solid, partial negative. And so the negative, right? So notice your negative is all attracted to those positive sodiums, right? So it basically surrounds and pulls away. And so now the chlorine is now all right, because now my negative is on the outside, because the positive ends of the water molecule have to surround that negative chlorine. And so in this way, this is what it looks like to have dissolved sodium chloride, right, which is going to be our NaCl EQ. Let me just erase that other parenthesis right there, right? So this is what, on the molecular level, is what salt water looks like. Every sodium particle is surrounded by the negative oxygen, and every negative chlorine is surrounded by the positive hydrogens of water. All right, so what is a network solid? All right, so when I think of something as a network, I think the word connected. Right, try to pick apart words and try to derive some meaning. So we have network crystals where all atoms are covalently bonded to each other, but in such a way that they are bonded in this network, it makes for a very high melting point and a very high boiling point for those. And they're very, very stable. Inert means unreactive, right? Our science with our big words. And some examples of those are sand, which is silicon dioxide, so SiO2, right? So sand doesn't really dissolve, right? And sand has an extremely high melting point and an extremely high boiling point. Oh, I already had that in there as SiO2. Okay, and diamond, right? So diamond is 100% carbon, but it is extremely strong, and it's because of how the molecules line up together, how every little particle lines up in what we call a network. So then it's basically a really, really strong, rigid structure. All right, let's recap our ionic bonding. Or let me see what I have coming up here. Nope, we're going to do that in our next video. All right, so we're going to end with network solids. All right, so the intermolecular attractions piece is a really important piece that's going to help us tie in some things together in our next couple of units. All right, thank you for joining me. Rewatch the videos if you need any reinforcement, or please reach out to Mrs. Midigar or myself if you have questions.